Not yet. Here I am. Here I am. Dr. Pilgrim, I have to apologize. I'm never late, and I'm not late per se, but I'm somewhat late because I was supposed to get online here about 15 minutes ago. But we are in COVID land nowadays. Last year, I had the pleasure of doing, I think, the very first virtual event of the symposium, and it was absolutely fantastic. I'd never done a virtual event, so we're kind of all veterans of that now. We all know how to Zoom and all of that, but a year ago I was a little new at this. And I'm going to tell you what, I was so impressed last year on how we did this, how Dr. Pilgrim did this, and I've been to some virtual symposiums since, and still it doesn't come to the standard that the symposium was last year. It was just fantastic seeing everybody's work, and it was just an absolute honor to be able to be the plenary speaker. So let me tell you a little bit about your next speaker. So I gave the talk of alligators to astronauts. I'm like, I want to give this long sort of thought about science, and you know, from last year I started as a field biologist, and here I'm at Embry-Riddle Aeronautical University, and I work with astronauts, and I mentioned my friend here, Dr. Fox. And so what a great way to start the next symposium by letting you meet her and learn more about what she does. So let me tell you, I'm going to actually piggyback on what Dr. Pilgrim just said about being intimidated when I first met Dr. Fox. So she's going like this. So I want to tell you the story. It's the funniest story. It still is. And so I was up in DC, and I was coming back to Embry-Riddle, and my close associate, Dr. Katrina, who, by the way, studies space weather, and so she brought Dr. Fox to campus. And so I went to my next appointment. I'm in an airport in Washington, DC, flying to Daytona, and I'm like, who is this person? Who is this person? And I'm really I got up at 4 in the morning, and I'm really tired, and I'm just being a baby, and I'm looking in my calendar, and I don't see anybody's CV, and I'm trying to find out who this person is, and I'm being more of a baby, and I'm calling up my people back here, and I'm like, who is this person? I'm gonna walk in, I'm gonna look like a dork because I won't know who this person is, and I'm type A, I'm type AAA, so of course I'm that annoying person in the airport who wants to make sure that she's in the front of the line so she can get on to the plane and be annoying to you. So that's me, and I'm on the phone, and finally people back here are like, I can't get her CV, but I found this YouTube video of her on a TED Talk, and I'm like, and so I'm being a baby again. I'm like, I don't watch videos. I don't watch videos. My teenager watches videos. I'm a scientist. I don't watch videos. So I'm like, whatever, I gotta watch this video. So I put on my iPad because I'm old. You know, you all use your phones, but I'm on my iPad, and I'm watching this TED Talk. And I'm like, oh my God, this woman's fantastic. Oh my gosh. And it was you will so enjoy listening to Dr. Fox and the people she works with today, and in that airport. So now I almost missed my flight. Miss Type A, who never, you know, I'm the first person on. I almost missed my flight because they called it this like last call. I run onto the plane. I'm like, okay, all right. So then I get there, and I'm in my conference room just down the hallway. I'm like, oh my God, what am I going to say to this person? Like, what am I going to say to someone so brilliant? Like, what am I going to say? All right. Like, I'm not going to tell her, like, I've worked with, like, radioactive biofilms, because that's totally boring. All right, I'll talk about the radioactive alligators, and maybe she'll think I'm somewhat cool. So I tell her, you know, about when I started as a field biologist on the Savannah River site, and I used to trap radioactive alligators, and she thought I was cool. And she's like, oh, that's really cool. And I'm like, I'm not cool, you're cool. So anyway, that started now, what, a 5-year friendship between us. I don't even know how to describe it. I'm just so lucky to have Dr. Fox in my life. I've learned so much from her over the last few years, not just about space, but about life in general. And you are going to have just a shimmer and glean of that. And you are the luckiest people in the world, like I am, just to be able to share this time with her. So, Nicola, it's all you. I'm going to just sit back here and enjoy your talk. So, how's that for an introduction? You're live.
I think I'm live. I can't see the red box, but I'm hoping I am. So, wow, that was quite the introduction. I'm really not that cool. But when you walk into a conference room and somebody says, "Hi, I wrestled alligators when I was in grad school," that's kind of a hard thing to deal with. I was just a little bit intimidated. But yes, Karen and I have been great friends ever since that moment, and so I'm delighted to be with you today to discuss a journey to the sun. And we're going to show you maybe a number of different journeys to the sun. One is our mechanical one, the mission that we sent to study the sun. And then I'm joined with some of my very favorite colleagues this morning who are also going to tell you about their journeys, their personal journeys, and how different they are, and how we all ended up in the same space, in quotes, space. So I'm going to jump into the presentation, and I wanted to start off with kind of a question to all of you, and so I hope that none of you are shy and you're all ready to put some things into the chat box. But I wanted to start off with just a question to you all of what do you think of when I say scientist? Kind of what do you visualize when I say a scientist? Because we sit here today, we're kind of accelerating into a future of virtual reality, climate change, gene editing, artificial intelligence, and of course the big discussion of vaccines that has come so important to all of us. And worldwide, I think we're really seeing a widening of the recognition of the need to build engagement with science beyond just the traditional idea of a scientist. So we all interact with science every day. Science helps you explain the phenomena around you, like how glaciers are formed, or how we get fruits from a plant, or how we have alligators in a swamp. Science enables critical thinking, and it helps us to critically analyze a phenomena or something that we're observing. It enhances our reasoning ability. It enables our adaptation, and it helps us face adverse situations, and it helps us face them successfully. Knowing the weather patterns and the direction of wind flow, you can determine the best possible place to camp, or to climb a mountain. Science has helped us in developing faster, better, and safer transportation. It keeps us healthier by giving us better information about infections, diseases, and cures. And it's helped save a large fraction of the world's population from food scarcity. So scientists also, the thing you're going to hear from us today is we get to use some really cool equipment too, such as things like the Large Hadron Collider, wonderful telescopes, and for us here at NASA, of course, our wonderful spacecraft. But the key to being a scientist is not to have all of the answers, for sure, but to love asking questions. So if you need to have a real curiosity and want to know more. And so if you are fascinated by how and why things work, you're already a scientist. I'm going to focus on exploration, because that's what we really do. And exploration gives us the sense that anything is possible. It leads us to knowledge and to understanding, and it means that you can make the world a better place as you explore. Now, humanity's interest in the heavens has been universal and enduring. Humans are driven to explore the unknown, to discover new worlds, to push boundaries of our scientific and technical limits, and then to push them even further. It's that kind of intangible desire to explore and challenge the boundaries of what we know, and where we've been, and how that has provided benefits to society for centuries. Space exploration really helps us to address fundamental questions about our place in the universe, and the history of the solar system. Not only that, but humans didn't evolve naturally to go into space, but we go there anyway. And that has led to the development of various technologies that feed back into the economy and improve our lives on Earth. For example, without space programs, you wouldn't have GPS, you wouldn't have accurate weather prediction, solar cells, ultraviolet filters in sunglasses and in your cameras. And there's also medical research happening in space right now, and I'm sure Dr. Gaines touched on that in her presentation last year. But that we could be finding ways to cure diseases and to prolong human lives. And a lot of these experiments just can't be done here on Earth. And space exploration really, therefore, could actually help to save your life. And so at NASA, we have sort of 3 key science themes that we work on. And all of our science kind of touches on each of these 3 themes. It's not like we all do things in a vacuum. We really do work together in a very cross-disciplinary way. So we have our 3 key science themes. You can see those there: discovering the secrets of the universe, the search for life elsewhere, and to protect and improve life here on Earth. And so we tend to focus at NASA on missions that address different areas of these key science themes. And so at NASA Science, in the science program, excuse me, we have sort of 6 main divisions. We have Earth Science, Heliophysics, that I'm going to talk to you about most today because I'm the director of the Heliophysics division. We have Planetary Science, Astrophysics, Biological and Physical Science, that is really focusing on a lot of the work that goes on the ISS right now. And then also a joint agency satellite division that helps us work with all of the other agencies in the US, and actually some international work too, because space really is for everybody, and it is a global issue that we work on together. So across these science areas, NASA emphasizes innovation and education. And so I like to think of these divisions as forming an interconnected community where science and technology develop together, and things that maybe develop in one area can often influence or benefit the other. And so we're really proud of our science organization. This is actually a look at the entire science fleet that we have in the Science Mission Directorate at NASA. And so I know that's an awful lot to look at, and I guarantee that there will not be a test at the end of this, but this is really just to show you where all of our missions are sort of located within the divisions. And so you can see all of the yellow things, they're clustered around the sun. You'll see in a minute, they're actually all over the solar system, but they are the missions that belong to heliophysics. In green, you can see all the missions that belong to Earth science. In blue, astrophysics, and purple is planetary. And then in orange, you can see all the things that belong to the biological and physical sciences. And so they are a lot of the missions that are going on actually on the ISS right now. So it is a very collaborative fleet. And we work, really across all of these. So even though we focus most on studying the sun and its impact on the Earth, we also look at the sun's impact all the way through the solar system. And so we often rely on data from our planetary colleagues to be able to sort of put together all of that data into one cohesive picture. And we also, of course, rely a lot on our work with Earth science as we kind of do the top side, everything that's coming in to the Earth, and they are looking at everything sort of from the Earth outwards. And so we collaborate a lot on the boundary between those two. And then, of course, with astrophysics, we study a star, we study the sun, but it is just an average star. And so we work with our colleagues in astrophysics to look at how the knowledge that we get about our sun can help them as they are studying stars in other galaxies. And so I'm going to bring you sort of back home into our galaxy. So if we start on the edge of the Milky Way, you'll see that spiraling around, and our sun is located on one of the arms of the spiral galaxy there, and you'll see us kind of honing in through interstellar space, and eventually you'll see our solar system coming into view. So you can see there the bright spot in the center there is the sun. And then there's a sphere around it. That's kind of where you think of as our typical solar system. But our the edge of our planets and where they orbit is not anywhere near the edge of our solar system. Our solar system goes far beyond that. But what we do see is the atmosphere of the sun, and you can see that as sort of a long kind of windsock shape. That is, as the sun is moving around in the Milky Way, the atmosphere of the sun actually carves out a protective bubble for our whole solar system. So all of our planets are protected from the vagaries of interstellar space by the sun's atmosphere. And at the very edge, kind of where that atmosphere is starting to peter away, it meets interstellar space and it forms an actual boundary. And that's what you're looking at there. And that is what we study with heliophysics. So the way we do that is with our Heliophysics System Observatory. And so these are all of the missions that we have in our portfolio right now. So we have 20 operating missions, 2 missions that we have that have just gone into development. So they've been confirmed and they are getting underway to really start building the instruments. And then we have 10 missions that are in formulation. So they are still in their very early phases, waiting to be confirmed as follow-up missions. The thing I wanted to point out here is just how vast our fleet, or the area of space that our fleet covers. So we go everywhere from very close up to the sun, Parker Solar Probe, which I'm going to talk to you about a little more in a minute. You can see a solar orbiter that launched just last year. That is a collaboration with ESA, the European Space Agency, that is working very closely with Parker Solar Probe. Parker Solar Probe in very close to the sun, making in situ measurements. Solar orbiter will be moving out of the ecliptic, so rising kind of a little bit higher up and looking down on the poles of the sun, so providing us with really great collaborative information. We have missions, you can see SOHO, ACE and WIND, that are out in the space between the sun and the earth. So they're kind of our advanced warning system. They are telling us when something from the sun is coming towards the earth and how it might impact us. And then we have a whole fleet of spacecraft. You can see those sort of around the planet in various locations that are really focusing on how what is coming to us from the sun is actually impacting our near space, our magnetic bubble. So we are also protected here at Earth by a magnetic bubble caused by the Earth's magnetic field. And then finally, I just want to point out the Voyager spacecraft. You can see those that are at the bottom of the image there. They are actually all the way out in that movie I just showed you that showed the very edge of our heliosphere, or of that protective bubble that protects our solar system. The Voyager spacecraft are all the way out there, way beyond the orbit of Pluto, all the way out actually in interstellar space. And so we use all of these missions together, and we use those to be able to really tell us everything we can learn about our star and how it impacts not just us here at Earth, but everything in our solar system. So it's really important to study the sun. It is for many reasons. One is it's extremely beautiful. It is a very, very active star. If you look at the sun, not that you ever look at it without protective eyewear, but if you looked at the sun in visible light, it's a fairly uniform sphere with maybe a couple of dark features on it. If you look at the sun here, as we are doing so in extreme ultraviolet, you can see the sun is anything but a uniform sphere. It is kind of a carpet of very intricate magnetic field patterns. Often these magnetic fields, you see them as loops. They explode, as you're seeing in the movie here, and they can send billions of tons of this material out into the atmosphere. We also study the sun because we literally live in the atmosphere of the sun. So the sun has an extended atmosphere. We call it the corona, and it is that part of the sun that is visible when you see a total solar eclipse. And yesterday actually marked three years until our next total solar eclipse that will be visible from the US. The last one, of course, in 2017. And I'm interested, actually, if any of you saw that eclipse in 2017. If you did, pop in the chat where you saw it, because it's always interesting for me to see how varied our people are that travel to see eclipses. So that outer atmosphere of the sun, the corona, streams continually away from the sun, and it bathes all of the planets. And so that means it carries all of the sun's energy to us here at Earth, where it can interact with us. Now, we didn't know that how closely the sun and the Earth were linked until 1859. And you can see a picture there of James Carrington, who was Richard Carrington, who was a British astronomer, and he used to sketch sunspots every day. He had a brass telescope in his home, and he would look through the telescope and sketch the sunspots. And he saw this particularly large sunspot group, which you can see in the image that he actually sketched. And while he was looking at it, the sunspot actually erupted. So he saw these bright flashes of light, and he actually likened them to fireballs on the sun's surface. He ran off to get a colleague to show the colleague and say, golly, look what I've seen. By the time they got back, the fireballs, or these bright flashes of light, had gone. And so they weren't really quite sure what they'd seen. But just a few hours later, the event actually arrived here at Earth. It caused beautiful auroral displays, like the ones that you're seeing moving now, but it caused them to happen at very low latitudes, so down much lower. Normally, if you think about seeing the northern or the southern lights, you're thinking about areas around the Arctic and the Antarctic Circle, not down at traditionally low latitudes. So certainly seeing an aurora in Florida, South Carolina, that would have been perfectly normal for this event. It was so big. It also caused compass needles to spin at the Earth, and the telegraph system, which was, of course, the internet in the 19th century. The telegraph system, there were sparks that flew from the wires, and the telegraph system itself went down and collapsed for about 4 days. And, you know, I often talk to my elementary and middle school kids, and I say to them, you know, imagine if you lost the telegraph system for 4 days, and they look at me like, yeah, whatever. But, you know, imagine if you lost the internet for a year or more. That is the kind of power that we see with our sun. And so it is really important for us to study that. And so here you're seeing an event that happened in March of 1989. So again, a long time ago, but it was an event that was about the size or very similar to the one that Richard Carrington had seen in 1859. And this event caused beautiful aurora to be seen very far south, but it also caused a widespread power outage. You can see the lights going off there in the Hydro-Quebec region of Canada down into New York State. And that caused people to be without power for a number of days. We did a study was done very recently that looked at an event that happened in July of 2012. And it was an event that went off the side of the sun. So it was not kind of looking down the barrel of the gun where you see an event and it's coming directly towards the Earth. This one actually went off on the side of the sun. It did impact one of our stereo spacecraft. And so we were able to take these beautiful images of the event coming away, and you can see a lot of radiation there building up in the camera itself. But we were also able to measure the size of the event because it hit one of the spacecraft directly. Using that data, we could then model what would have happened at the Earth had this event happened just 1 week earlier. And the estimation is about $2 trillion worth of damage that would have been caused by this event alone. And so as we become more and more reliant on technology, you know, none of us ever think about taking a map with us anymore. We just plug into the phone wherever we're going, and Waze or whatever your favorite app is will take you to where you need to be. You make your airline flights using your phone. You make your hotel reservations using your phone. You do everything using your technology. And so if we had an event that was this big now, it would have a far greater impact than knocking out a telegraph system for 4 days, because at that time, that was the only technology that people really used. Now we would be crippled for long periods of time. So it's extremely important to us that we really understand our star. And the way we want to understand our star, we've got some long-standing mysteries of solar physics. And these mysteries have been around for decades and decades. The first one is, why is the corona hotter than the sun's surface? And so if you watch the progression of this movie, you'll see here is a measurement of the temperature of the sun's visible surface at about 6,000 degrees. As we start moving away from the sun and getting further away from the sun's surface, instead of the sun getting cooler, as you would expect, you know, if you walk away from a campfire, you certainly get cooler, not hotter, as you move away from the heat source. In the sun, it's actually the other way around. As you're getting further away from the sun's surface, you get up to a maximum that's about 300 times hotter than the surface of the sun. And so that means there has to be some physics, there has to be some processes, something that is going on in this region that is causing this intense heating, and also the power for this plasma itself to get accelerated away from the sun. And when we say plasma, we're talking about like the fourth state of matter. So it's like a superheated, really energetic gas that is so energetic that the gas kind of splits apart and goes into its initial constituents, so into its protons and electrons. And that is, so it's so superheated that we see the sun's atmosphere as a plasma. So that is one of our mysteries. Why is this corona so much hotter than the sun's surface? The other mystery is really, why does it accelerate away from the sun? And so you can see in the graphic here, the kind of the atmosphere of the sun, you see the sun in the background there, but the atmosphere accelerating away, bathing all of the planets. And that actually causes, it actually helps us, our magnetic field protects us. You can see it sort of diverting that flow of energy around the Earth and keeping a lot of that harmful radiation away from us here at Earth. But what we really want to know is, how does this solar wind, as we call it, how does it originate and how is it accelerated such that it actually has the power to impact our planet, to actually cause these large space weather events? And then the last one is, how are solar energetic particles accelerated? And so we talk about this sort of solar wind, these features that are kind of continually flowing away and Earth, but we also see some very intense energetic particles that are accelerated, and they're usually accelerated due to shocks or like transient phenomena that we see in our solar wind. And we really want to understand how they are accelerated, because they are not totally protected, or we are not totally protected from those by our magnetic field. They can actually penetrate through and cause issues for, certainly for astronauts, and as we continue on our journey back to the moon and then onto Mars, we want to make sure we're protecting our astronauts. We want to understand how these energetic particles are formed, how they're accelerated and transported. Of course, they also impact technology. They can really cause a lot of damage to spacecraft in orbit, both to their electronics and also to their solar cells. And so they are our three kind of long-standing mysteries of solar physics. And I say they're long-standing because we first wanted to study these phenomena back in 1958. And you can see James Van Allen there. So this is right after the launch of Explorer 1. And so that was really the beginning of the space age for us here in the US. We discovered space wasn't empty, it was actually very exciting, and there were lots of interesting phenomena there to be discovered. Also in 1958, a paper was published by a then young scientist, Dr. Eugene Parker, and he published this sort of seminal paper that predicted exactly what we see today. It predicted this continual acceleration and expansion of the solar atmosphere such that it would impact us here at Earth. His paper was a little controversial. A lot of people did not agree with him. He likes to tell me that, you know, one of the reviews he got back said, golly, if you're publishing in this area of physics, you should really go to the library before you publish your paper. And then he likes to smile and say, and that was the good review, Nikki. So luckily for us, the editor of the journal thought this was a very controversial paper and it should be published. And it actually led to us wanting to not only study space, but to really go in and study the sun's corona. And so the committee that was formed, you saw that in that very beginning clip there, they came up with 14 proposed missions that were sort of really groundbreaking and really needed great thought and planning. One of those was a probe to go into the sun's atmosphere, and it has actually now launched, but it was the last of the 14 to be able to kind of come into reality. And that was just because it was a very daring mission, and we had to wait a long time for our technology to kind of catch up with our dreams. We knew what we wanted to do as scientists, Even in 1958, those questions that I just went through were 3 incredibly prevalent questions that scientists of the day then really wanted to study. They remained the highest priority for scientists, and so we worked, teams of people, I mean thousands and thousands and thousands of people worked on different concepts and different ways to be able to enable this very daring mission. And so this is what the mission looks like. This is Parker Solar Probe in an animation very close to the sun, and you can see a nice view there of the spacecraft. So it launched recently, well, just two and a half years ago now, and we're getting all of our data back now. So we're very excited about the science that this mission has enabled. But I know we've got a mix of scientists and engineers and also non-scientists with us. So I wanted to talk a little bit about the technology behind Solar Probe, because we really needed these transformational innovations to be able to allow us to do this kind of mission. And so I'm going to touch on a couple of the sort of big things we needed to do. One was to protect the spacecraft from the heat. We're going incredibly close to a very active star. It's in the spacecraft itself is traveling through 3 million degree plasma. Now the plasma is not too dense, and so we don't get a lot of heat that couples directly into the spacecraft. If you think a bit about turning on your oven to 450 degrees, let it heat up, you can put your hand in the oven and you won't get burnt unless you actually touch something, unless you touch a surface. But the atmosphere inside the oven itself is not as dense, and so you can put your hand in there and you won't get burnt. But as soon as you touch something and you let that heat couple into your fingers, then you're going to get a very nasty burn. So I don't recommend trying that at home, by the way. So we actually needed to develop materials that would be able to withstand the heat. Also, as we'll talk about, we use Venus gravity assists. We fly past the planet Venus to help us trim our orbit and get closer and closer to the sun. And so it's not only the intense heat, but it's also very cold. And so the spacecraft makes petal-shaped orbits close to the sun on one side, out around the orbit of the planet Venus on the other. And so it is continually getting hot and then cold. And so if you think about any material, if you heat it and cool it over and over again, it will actually change its property. It'll either become like elastic, or it can become brittle and actually sort of break. And so we need to have materials that do not change their property. So we have a thermal protection system that sits out proud of the spacecraft. That's made of a carbon-carbon composites. It's a little bit like a graphite epoxy that you might find in your bike or a nice tennis racket or a set of golf clubs. That really durable material, but it's much lighter than traditional materials. On the front side of the spacecraft itself, you can see there it's glowing red. That's because we're depicting having to deflect the heat. It's actually a whiter than white coating, and it was a plasma sprayed alumina. It's a little bit like a ceramic coating, and that actually helps to reflect most of the light. And so really what we're worried about is we're so close to the sun that most of the heat that we're experiencing is actually from the photons, from the light from the sun. And so that actually reflects a large amount of that light away. And so the front side of that heat shield gets to about 2,500 degrees Fahrenheit, or about 1,400 degrees Celsius. And the main body of the spacecraft is only at about 80 degrees Fahrenheit, 30 degrees Celsius. So kind of a balmy evening, I guess it would be in Florida, but sort of more like a traditional summer's day for us here in Washington, D.C. We also had to find a way to cool our solar panels. And so one of the big challenges for us was we did not have any kind of nuclear power system, no RTGs. We had to use the power of the sun. And so people look at me like, well, why is that a problem? Nikki, you're going to the sun. Surely solar panels are going to be easy to use. But as all of you who will know, if you've left your phone on the front seat of a car on a summer's day, it is not very happy. It will power down and it won't work, and it needs to cool down, because all sensitive electronics do not like to get hot. And solar panels in particular do not do well if they overheat. They become a lot less efficient. So we had to find a way to actively cool our solar panels. We do that in two ways. One, we actually have them, they're fully articulated, and so they're kind of on like shoulder joints, so they can stretch out to their full expanse when we're out around the planet Venus. And then they tuck all the way in until just one row, kind of like if you think about the very tips of your fingernails, just one row of solar cells is actually exposed. And we get the same power from that one single strand of solar cells when we're close to the sun as we do from the full wing when we're all the way out. So that kind of gives you, again, another idea of how close we are. In addition to that, we also run water through the solar panels, and it's if you think about veins running between each of the solar cells, so the water runs through there, cools the solar cells, and then we radiate that heat out from actually behind the heat shield. We have a radiator system that sits there. That is an incredibly complex system that we had to design, especially for Parker Solar Probe. Also state-of-the-art instrumentation, and it was really we've got this exposed solar probe cup, and one of my friends that I know is going to talk to you a little bit about that because she worked really extensively on that instrument to deliver it for our mission. But it was a very unique instrument. It was actually a very simple instrument. It was one of the first types of instruments to fly, a Faraday cup, but it never had to fly in this full solar atmosphere. And I like to refer to this instrument as the bravest little instrument because it does not sit on the main body of the spacecraft, taking a sort of in the shadow of that big heat shield. It actually sits out the side, and you may just be able to see it on the left-hand side, kind of the middle, right in the middle of that diagram. You can see a little circle sticking out of the side of the heat shield. That is the solar probe cup. And that instrument sort of peeps around the heat shield and looks out in the full intensity. So we had to use very special materials that had melting points of exceeding 4,000 degrees Fahrenheit. They also had to find a way to suspend their wiring so that the wiring didn't melt. And so they used sapphire crystal tubes to actually suspend it. So even though it was a simple instrument from a mechanical point of view, actually designing it to fly on this mission was extremely challenging. And the last one I'll just touch on is how smart this spacecraft is. I always describe her as kind of a fiercely independent spacecraft, but if you think it takes light 8 minutes to travel from the sun to the Earth. So if this spacecraft has a problem, there is no way that we can get a signal back from the spacecraft, digest what the signal is here at Earth, figure out the problem, and send a command back, because it would be too late. If the spacecraft starts to in any way turn, the important thing is to keep that heat shield between the sun and the Earth sun and the spacecraft, sorry, at all times. And so if there's a problem, she has to be able to look after herself. And so there is an incredible amount of smarts built into that spacecraft. It's kind of think about like a sort of a what if scenario, but thousands of them. So, what if this happens, then do that. And so it's this sort of if then statements that are programmed into that spacecraft for every possible problem that we could envisage her having before launch. And so they're just some of the transformational innovations that we had to do to launch this mission. I can't talk without showing this absolutely beautiful movie of the Parker launch. And so this is happened August 12th, 2018. It was 3:31 in the morning from Kennedy Space Center. Some of you may have actually been able to see it. If you're in Florida, I know you could see the trajectory of that launch vehicle. There is Solar Probe out, lifting off. The second stage, that was a Delta IV Heavy. So we used every single ounce of power in that rocket. You saw a custom upper stage there. The spacecraft then lifting off. This all happened in about the first 35 minutes after launch. First thing we do on orbit is to stretch out those solar wings to get power to the spacecraft. And then we start to deploy all of the instruments. And you can see the instruments, various different locations. They are radio waves. Nice shot of the Solar Probe cup there also. We were moving very fast. Just about 6.5 weeks after leaving Earth, we encountered the planet Venus for the first time. We use Venus to do some gravity assists, as I mentioned. So we use Venus, we kind of We give energy to Venus. We don't take energy from Venus. We actually give it to Venus. We use it to slow down just a little bit and kind of tilt that orbit in. So we sort of trim it to make the spacecraft go in towards the sun. You saw those kind of petal orbits there. We will do 7 Venus flybys over the duration of the mission, each one taking us closer and closer to the sun's surface. I'm going to pause and see if there are any questions that you want me to answer.
Yes, Dr. Fox, we have a question about the space probe that you have going around the sun you're speaking about currently, asking if the heat shield were conical instead of the flat model that you have, would it stay cooler?
That's that is a great question. There have been many different designs of the solar probe over the 60 years since it was first thought about. There have been many different designs, and one actually did have a conical heat shield on it. It looked very much like a cone shaped, and the whole spacecraft kind of was inside there. There are many different designs. This was the one that actually worked the best for us. What we actually want to do, the reason we have it flat like this, is we want to keep the amount of heat as uniform as possible over that front surface to enable us to deal with it. And so actually one of the reasons is everything is plasma sprayed is we don't want to have any slight bubbles or slight higher density of even the reflective coating on there. So there have been designs that did use a conical heat shield. They also actually had different orbit trajectories. They were going even closer to the sun. But for this particular way we designed this mission, we needed to keep it totally uniform across the front. And so that was better achieved with a totally flat heat shield. But that is a really great question. Maybe if we do Parker Solar Probe 2, whoever asked that question could come and design a new heat shield for us. How about that? Any other questions?
Not currently. You did have a few people tell you that that where they were at the eclipse, but we can address that at the end.
All right, that is great. Okay, then I will keep going because I do want to make sure I get time for my friends to also talk. So, you know, I always like to say we're not competitive on Parker Solar Probe. We're just hotter, faster, and closer than anything else. So we have broken a huge number of records as we have gone. Where we are right now is we have done 7 flybys of the sun. We've done, that was using 3 gravity assists. We just completed our 4th gravity assist in February of this year. When we did our top speed, going past the sun on our 7th approach, we were traveling just shy of 290,000 miles an hour with a distance from the sun of about 8.4 million miles. Now the sun and the Earth are 93 million miles apart, so that's pretty close. We just completed, as I said, the 4th of our 7 Venus gravity assists. And so that will set up Parker Solar Probe for her 8th closest approach, which will happen later this month, actually on April 29th. And during this pass, the Parker Solar Probe will break her own speed record, and she will come, and also her distance record. She will come to about 8.5 million miles of the sun's surface. That's about 10.4 million kilometers. Now at closest approach, when we get to our final closest approach, so that is after the 7th Venus gravity assist, we'll be hurtling around at about 430,000 miles an hour. So it's about 700,000 kilometers an hour. That's about 118 miles a second. And so I can just about get my mind around 118 miles an hour. This is moving at 118 miles a second. So that actually will take you from New York to Tokyo in well less than a minute. We are deep in the heart of the corona, so of course we are the hottest thing. I already talked about that heat shield dealing with temperatures of about 2,500 degrees Fahrenheit, 1,400 degrees Celsius. Actually, the whole spacecraft in plasma, that the individual particles actually measuring about 3 million degrees. And we're going to be closer. So at our our last closest approach, we will be at about 3.9 million miles above the sun's surface. And when I say 3.9 million miles, a lot of people don't think that's particularly close. And so I love this graphic that actually my friend Kelly, who you'll be talking to in a minute, also did for me. But putting the sun and the Earth on either end of a football field, put Mercury at the 35-yard line, Venus would be at the Earth's 28-yard line. Some of those really beautiful coronal loops can extend out to about the 15-yard line. Up until Parker Solar Probe launched, Helios 2 was the closest mission that had gone into the sun, and it got as far as the Earth's 29-yard line, so inside the orbit of Mercury. But then Parker Solar Probe, which is our newest mission to study the sun, launches and will tuck and run all the way to the sun's 4-yard line. So in the red zone, knocking on the door for a touchdown. So the sun there, the spacecraft there studying the corona by flying right through it. And so I want to just finish by looking at a couple of the science results that we've had so far from Parker Solar Probe. So one of them is there a dust-free zone around the sun? And we know that our solar system is awash in dust. It's kind of like the cosmic crumbs of collisions that formed planets, asteroids, comets, and other celestial bodies billions of years ago. But almost a century ago, Henry Russell, the scientist, predicted that there should be a region around the sun that was devoid of dust. And the reason for this is that large particle dust far away from the star go through kind of a grinding process due to collisions. And so therefore, the closer we get to the sun, the smaller the dust particles will get. And the smaller particles of dust get heated much more effectively than large ones. And so at a certain distance, these particles will get so hot to the point of evaporation. And they're also subject to frequent collision with solar wind ions too. And so this whole sort of evaporated material can get carried away under the effect of the solar wind, which will result in a dust-free zone close to the star. Now, we've looked for the zone for decades, but of course, we can't see it because we're looking through the dust. But Parker Solar Probe is getting close enough that our cameras can actually look into this region to see if there's actually a dust-free zone. And so this is data from our camera, the Whisper Imager, which is looking at, it's a white light imager, and it actually images the solar wind. So it images this atmosphere coming towards us as we're moving in and out of the orbit with the spacecraft. It's a little hard to see, but what you're looking at is mostly dust scattered light. And so they're plotting the intensity of the light there. You can see it's brighter as we're further away from the sun. As the spacecraft gets closer, you can see the actual intensity of the dust dropping away. Also, it's a little bit hard to see on this plot. There's a blow up there, but we looked at this is data taken from the spacecraft compared with a model. So the model there would give you, that's the sort of dashed cyan line, would give you the measurements that we see of dust here at Earth. And if we just sort of take those straight back to the sun, what we would expect to see, we'd expect to see dust. What Whisper is seeing is you can see that curve is starting to turn down. And the insert there is displaying the departure of the model from what the camera is actually seeing. And so we are looking at there's the percentage of dust there. And so you can see instead of being 100%, we are tracking down to about 65% of the dust. And so as we continue to get closer and closer, we expect to see that depletion number continue to come down towards zero. And we're hoping that when we get to closer to the sun, so we can look even closer, we will actually be able to fully see no dust at all. So that should be at about 2 to 3 million miles from the sun. Of course, our camera has a bigger field of view. So even though we are at about 3.9 million miles, our camera field of view can look into that 2 to 3 million mile mark. And the other exciting discovery for us was something we called switchbacks. These are S-shaped curves in the solar wind, something that we've never seen before because we've never been close enough to actually see these structures. And so you're looking at like magnetic field lines, and these switchbacks think about taking a garden hose and putting a twist in it, putting a kink into it. You have to put energy in to kink that garden hose. The first thing it wants to do is spring apart and let the energy back out. And so what we're seeing is the release, these S-shaped curves, putting a lot of energy into the corona. And so it could indeed be a source of heating. So one of those mysteries, why is the corona so much hotter than the surface of the sun? Here's a mechanism that is providing coronal heating. Of course, we still have a big debate on what is actually causing these switchbacks. So, you know, you go and you make an observation of a new phenomenon. Now you have to explain what is causing it. And there are certainly a lot of debate over whether it's happening due to sort of magnetic explosions that happen in the sun's atmosphere, and other people that think it's turbulence. So it's, if you think about throwing you know, a rock into a stream and you see all the turbulent flows that occur, other people think it's just turbulence that is there, and some scientists of course believe it's a bit of both. But that debate will go on for a little while longer as we continue to explain why that corona is so much hotter. So I'm going to finish with just some statements about my own journey to the sun. You know, you can see me with Parker Solar Probe. So this was sort of the crowning jewel of my career, was being the project scientist or the lead scientist for the Parker Solar Probe, and it was a totally awesome job. You can see I'm there in my clean room garb, in with the spacecraft. You see the spacecraft behind me, and the bottom there showing Eugene Parker. So I mentioned at the beginning that there was a paper in 1958 that was published that led to the real drive for this mission. And it also made the mission very historic because it was the first time that NASA named a mission for somebody during their own lifetime. And so you can see me there standing behind Gene at the launch, watching his spacecraft, the spacecraft that bore his name, go up into space to really brave this atmosphere of the sun. But my main responsibility was to ensure the scientific integrity of the mission. So in other words, to make sure that the mission returned the necessary information that all the scientists have been waiting for all this time to answer all their questions. And so I led a great team of scientists from all over the world who helped plan the science goals and now anxiously await the receipt of every single bit of data to really help us study the sun. The way I got there was not a simple, straightforward path, and you'll hear we all had different ways of doing this. I would say, you know, there was no one thing that first sparked my interest in science. I just always loved it. My father will tell you that it was his actions when I was 9 months old. Neil Armstrong walked on the moon, and he took me out of my crib where I was sleeping and propped me up and gave me a running commentary. And so he takes full credit for my interest in space. But my interest in science has always been driven by something much more than just one single event. I always really liked the logic of it, and there was, you know, always a reason why something happens, and so many mysteries to solve. I went to an all-girls school, and I was actively encouraged to study science. I knew I wanted to be a scientist, but I wasn't quite sure what type. I discovered very quickly I fainted every time we had to do dissections in biology. I don't like the sight of blood. I'm pretty squeamish, so biology didn't really seem like a particularly good thing for me. I had still one of my best friends, but my lab partner in chemistry was really crazy. She would blow up test tubes, spill concentrated acid on herself, leave the fume cupboard door open, just all these kind of nightmares. And then she announced she was going to go do chemistry, and I thought, that sounds a little dangerous. If there's one like her, there's probably more. So I always joke that I took the safe option of physics. I always really loved astronomy too. I went to Imperial College in London. I studied physics as an undergraduate. I didn't do particularly well. I suffered greatly from imposter syndrome, and I really didn't feel that I didn't feel that I was fitting in. I didn't enjoy it, and I thought that maybe this was not the field for me. So I went to do a master's at the University of Surrey. I did a master's in telecommunications and satellite engineering, and I quickly realized there that I was definitely a scientist and not an engineer. I was regularly told that I asked the wrong questions and I thought like a scientist. And so I returned to Imperial College, where I completed my PhD in space plasma physics. And after that, I moved to the US, where I took up a postdoc position at NASA's Goddard Space Flight Center, where I studied all the aspects of the Sun-Earth system and started working on missions. From there, I moved up to the Applied Physics Lab, and I was there for nearly 20 years and worked on a number of missions there, the highlight, of course, being Parker's Solar Probe. I have 2 children, so they are 11 and 13, so they keep me very, very busy. And one of my biggest challenges that I have is balancing work and home because I travel a lot and I work an awful lot. But I also obviously want to be a really good mother, and so I try and be as involved in their lives as much as possible. I volunteer at the schools all the time, and I do a lot of STEM events with them so I can bring kind of work in. They also get to travel to all of the launches that I support, so I think they've been in more control rooms than any 2 children ever should. Today, I'm the director of the Heliophysics Division, and so I lead NASA's efforts to explore the star that makes life possible on Earth. Scientists that study heliophysics are really looking at how the sun impacts our planet and the rest of the solar system. I always think ever since people first looked up, they've wondered about that bright light in the sky. They've wondered what it is and how it works. And so, heliophysics really is the oldest science branch that there is. The interesting thing about my job is that every day is different. There are always new challenges to face. I get to work with hundreds of scientists and engineers. I love learning new things from them every day. You're always trying to discover something new. And I'll just note that the people that work on NASA missions are highly skilled professionals. They're dedicated to their work. And when issues arise, they just deal with it. They come up with a plan and they implement it. And so there's nothing better for me than working as part of a highly performing team. The missions are fantastic, the technology is good, the science is awesome, but it's the relationships that you make in life with the people that you work with that really stay with you for the rest of your lives. And so with that, I am going to hand over to some of my friends to tell you about their own journeys to where they are today. So I'll start with my friend Ali, who's going to take it away.
Hi, good morning, everyone. So Ali Mendoza Hill. Obviously, I'm in a tough position following Dr. Fox, but I met Dr. Fox 2 years ago when I came up to the Heliophysics Division on a detail. But I'll tell you a little more about that. I'll try to fill in the shoes. Anyway, this is a very busy chart. But actually, it's the story of my life. I'm not going to obviously go through every detail because I'll take 3 hours. So I've got 5 minutes and I'll try and go through the highlights. Pretty much I started working at the age of 14. I was a welfare kid. And so I made the choice at a very young age that I would do everything I could to live above the poverty line. How I was going to do that? Education. It might have been easier for me because growing up, I loved sports, I loved math, and I loved how to figure things out. But like Nikki said, there wasn't an aha moment where I knew what I was going to do. I wanted to do everything. In school, I knew I had to do more than the average kid because I knew I needed to get scholarships if I wanted to go to school, if I wanted a continued education after high school. My mom couldn't afford college, so it was the only way I could ensure that I could get someone to pay for my school was to be the best at everything I could try. So I'll fast forward to high school graduation. Lots of hard work and stuff. I ended up with 3 choices. I know now that any of the 3 choices I would have been successful at, but I chose to stay at home, and I had a full ride at University of Miami in engineering, which is I knew I wanted to be an engineer or an astronaut or a fighter pilot. I like things that went fast. I like to do things. I had 2 older brothers, probably what headed me in that direction, fixing our own cars, fixing my own bicycle. We didn't have money to pay for someone to do it. So I'll fast forward through college, 3 engineering degree changes. At least I stayed within engineering, so it didn't impact me too much. But about 3.5 years in, I decided to take a break. I wanted to become a beach bum. I played professional beach volleyball. I made money. I worked for an exotic car dealership selling Ferraris and things. But after about 6 months of that, I said, I need to go back. I need to finish what I started. This isn't going to get where I wanted to be in life. But it took a little bit of, thoughts. It was easy in Miami to just live the beach life and stuff. But I decided to get back on track. Graduated with my industrial and systems engineering, started working as an IE consultant, an ops manager, really busy at work. About 5 years later, I get a phone call. It's from a university professor. I had been her research assistant, but I also had done a few projects, senior projects, while I was in the university. One of those projects was a NASA research grant. It was a 6-week project to build a statistical tutorial for NASA engineers. Nothing major, but did it, as part of your standard university tasks. But she had become a professor that was on sabbatical at Kennedy Space Center, and Kennedy had opened up positions for industrial engineers. So she reached out to me. I said, oh yeah, whatever. I applied. And next thing I know, I'm at NASA, in the year 2000. So I moved up from Miami, made my way north 200 miles to Kennedy Space Center. Next slide. So then comes the last 20 years of my career at NASA. Amazing. I've had, my first 10 years was in human spaceflight. You could tell by the pictures, I've done a lot of cool things. Never thought this is where I would reach. You can see where my offices were. I was right there in the thick. I saw space shuttles every day. I became the vehicle manager for tank and booster. I worked in the marine ops. I worked with the, oh, that's my little motorcycle. I did say I did like fast things. So balance life and job, worked a lot, but enjoyed life as well. It's a key. 10 years later, I had the opportunity to switch over at the end of shuttle. Once we closed out shuttle, I switched over to the launch services program. Little key thing, my manager for the last 10 years was the contract officer. She was the supervisor of that project I told you I did back in 1994. So fast forward 15 years later, now she is my boss. Just for a little university task project that I worked on. So just things go and come around in circles. But this was amazing because I went from human spaceflight to launching science. Cygnus was hurricane hunters. OCO2 was carbon dioxide monitoring. Small satellites to go see how we can protect the planet from asteroids and DART. InSight, sent a lander to Mars. Pretty much I was launching 4 different rockets at some point of those 10 years. It was really amazing. At each point, I thought I had the best job in NASA. Fast forward to a year ago, I end up moving up to Washington, D.C. and working for Nikki as a detail in rideshare. Rideshare is where we want to use the excess capacity of these launch vehicles. So that fairing is really big. So could we launch 2 or 3 satellites or more, all for the cost of 1 rocket? So I've moved on, and here are some of the missions I'm working now. Escapade, going to Mars, Glide, Solar Cruiser, Janus. They're all different types of missions, whether they're Mars missions, solar missions, Earth missions. They're really all exciting science, something I would never thought back when I was in college that I would be working. Next slide. So my takeaways. I had to make a lot of choices throughout life, and it's okay. I thought I had a road plan. I thought I knew I wanted to be an astronaut. I knew where I had to go, but things happen. Your plans get derailed by life, and it's okay. You stop, you think, you don't, but just don't give up. There's always a speed bump. Just think about it. Find an alternate path, do something, but always make sure that you self-awareness. You think through your decisions. It's okay to make the wrong decision, but don't make a bad decision. If you've ever heard that, you never know what the path will be after you make a decision. As you saw my path, I could have gone in different ways, but as long as you think through it, that's what you should do. Think through self-awareness. What do you want? What do you love to do? And move forward. Obviously, take on assignments in college. That's what got me to NASA. It's just a simple project at school, and ended up with two contacts, and that's where I am today. So you never know what experiences open up in the future by just taking those opportunities. Diversify yourself. I was always great at whatever. I tried to be great at whatever I did, and I liked everything. So I was like, I did different things. But if you're going to be a top-notch scientist or engineer like Nikki, you could also see that she is great at communicating and passionate about what she does. It doesn't matter what realm of science. You got find your passion and follow it, and be able to communicate it to others. And obviously, education. I mean, we said we continue to learn. After 20 years at NASA, I'm up here with Nikki, and it's amazing. I mean, look at you saw the images. It is exciting. I always loved the sun. I was a beach bum, but as a rocket scientist, I just wanted to launch those satellites. Now I'm like, hey, I really like solar physics. I really like this space weather things. I am learning so much from everybody around me. It's just pretty fascinating. So yeah, eventually I didn't become an astronaut. Didn't matter. I still love my job, and I still play a role in improving our life, here on Earth. That's my takeaway. Do what you want. be passionate about what you like. That's it.
All right, David.
Hello, everybody. My name is David Cheney. You can go ahead and go to the next chart. So I'm going to start a little bit before this with my schooling history. I went to a high school that had less than 200 students. We didn't have much in the way of science opportunities. We had biology and physics and chemistry, and that was about it. You couldn't get any extra science or any extra math. When I decided to go to college, I went to a junior college first, because going from a high school of less than 200 to a school of 35,000 seemed a little overwhelming to me. So I chose to go to a junior college and got an associate's degree first. Then after I graduated there, I went to Brigham Young University. In between, I also got married. So I was going to school and married, and that was a challenge, but we were able to make it through. And I earned my way through school, so I didn't have any extra help otherwise. I got scholarships and got a job and worked and made my way through school. Married, and by the time I graduated, we had 2 children. So that was a challenge, but we still were able to do it because we kept focused on it. For my last year of school, I actually was doing school for physics education. So as my last year of schooling, I got an internship teaching at a junior high school level, teaching science. And while I was there, that last year, I got a letter from the Navy that invited me to consider becoming an instructor at the Navy's nuclear power school. That was something that I had been interested in high school, but I didn't think that I was going to be able to do that. But talking to my wife, we decided that was a good opportunity to try. So we explored that opportunity. I got to teach one more year of school, teaching math and physics in high school, and then I joined the Navy, which was not something that I had really been planning on doing. But the initial job of teaching in the Navy was only supposed to be a 4-year commitment. So we were supposed to teach for 4 years and then go do something else. And that had been our plan. And then after I was in the Navy for about 2 years, they decided that they wanted to keep all of us as instructors that they brought in, and put us in other jobs that they thought they could find useful for us. So I started looking at other jobs within the Navy that would sounded interesting, and I found meteorology and oceanography as an option that sounded really pretty exciting because I got to continue doing science, and I wanted to make a difference. So most people don't think people forecasting the weather are very good at anything, but we do get to make a difference. So I lateral transferred over to doing weather forecasting for the Navy. If you see the next picture on here, this is a picture of Hurricane Katrina. So some of you probably remember this one. I remember where I was. I was actually on watch that day when we were working with the National Hurricane Center and deciding that we needed to send out a warning for the Hurricane Katrina, the formation of Hurricane Katrina. One of the things we had as our job in the Navy as a forecaster was to make sure all the ships at sea were safe from the hurricanes. The weather around hurricanes it's pretty bad on land. It's at least as bad at sea. You have to be quite a ways away so you're not don't just get rolled by the waves and sunk. So that was one of the things that we spent the next several days doing after forecasting and seeing the formation of Hurricane Katrina, is making sure all the ships were out of the way, which was a real challenge because that one didn't go where people were expecting it. And so basically we were told everybody in the Gulf of Mexico, you had to get out. So they quickly sprinted to the far reaches of the Gulf of Mexico to try to get out of the way. I got to do that for several years in the Navy, just forecasting weather and helping keep ships safe from the weather at sea. After doing that for several years, I went to Naval Postgraduate School and got a master's degree in meteorology and oceanography. And then my next assignment was on the USS Enterprise, which is pictured there. One of the cool things about the USS Enterprise to me is I taught nuclear power, and this was the great nuclear power experiment for the Navy. They said, well, the Admiral Rickover went and had to convince Congress that they needed to spend some money and create a nuclear-powered aircraft carrier, and that it would actually be able to last for 50 years if they did that. But the part of the challenge was they didn't know how to build it, or they didn't know how to do that and what kind of requirements they were going to have. So they took 8 submarine reactors and put it on the aircraft carrier to power it. And so I actually got to drive the aircraft carrier out of port on its last deployment, which was really fun. So I got to do that. It was really cool to be able to participate, both understand the physics and what was going on with the reactors, but being able to drive it and doing that part was really pretty cool. And so if you're wondering, if you've ever seen the Enterprise, that's actually the most likely ship to be found in movies. If you see movies that have aircraft carriers in it, then the Enterprise is actually the most likely one to be found in those. Most famous is Top Gun. It was filmed on the Enterprise. So it has since been deactivated after 51 years of service. After I served on the Enterprise, I got to do another job that just seemed really interesting, but didn't seem really like what I'd been doing before. I was doing imagery analysis, and climatology, and then I went to the DoD space test program where I got to do some space stuff. It's like, okay, this is new. The Navy said, well, we've got people that understand basic science stuff. We have these meteorologists that we sent to school. They're probably the most likely ones to be able to understand the space stuff. So we're going to send them to do this. So that's one of those jobs that you get just because you're likely the only one that's going to understand what they're talking about. So I got to go do that. We got to design spacecraft. We got to design missions, set up launch opportunities for the spacecraft. All these were experiments. So this the goal of the DoD Space Test Program is to launch experiments for the military to find out what kind of instruments work in space, how do they work, how well do they work, does this work to actually measure this? So that entire program, the DoD Space Test Program, was to find out whether or not the engineering and the science would work. So I did that for 3 years, and then I finished my naval career at the Naval Research Lab, where I worked in the remote sensing, and got to learn about all kinds of other ways of doing remote sensing as well. I retired from the Navy in June, and kind of on a whim, I applied for a job at NASA, and in hopes that I might be qualified to work at NASA. And I was really excited to get a call and an interview. So, but that whole process happened virtually. So that was very, I have yet to actually physically meet Nikki or any of my other colleagues for that matter. So that's an interesting way to adjust to a new career. Since being at NASA, I'm a program executive. I work on an atmospheric waves experiment that is measuring gravity waves in the atmosphere. So gravity waves are just, think of like ocean waves, but they're actually in the atmosphere. And then the polarimetric, the punch is another one that we're going to be measuring different aspects of the sun from four different angles, so we can see a lot of different things that are going on the sun. And then I also manage 19 CubeSats, which are getting ready to launch. So some of these have, all the ones in green actually have launch dates. And then you have a couple challenges, but that's what I do at NASA. All right, next slide. So one of the things I found for myself in my career is that I, love the job that you have and learn from it as much as you can. I've in all of my jobs, I've been able to use knowledge that I gained from all of my previous jobs to help me do the one I'm in now. Every 2 or 3 years in the military, you get to learn a new job. It's like starting a new career every 2 or 3 years. So you get to learn a new job, you get to learn new things from people that you're working with. And it was a great opportunity to learn from all these different people. So I really enjoyed doing all these different careers and starting this new one. So one of the things that I think is interesting is I worked to help pay for college. I worked at a gold and silver mine, and that knowledge that I had actually helped me in my work as an imagery analyst, which was something that I would never have put the two together. So, for my advice is that any work experience you get can help you in your future career, and to just keep going and learn from whatever opportunities you have. And that's all I have. Thanks.
Hello, my name is Dr. Kelly Korrick, and I am a program scientist at NASA headquarters working with Dr. Fox. And so my career right now, or has led up to this point in time, started with some rockets. So this is me in the deserts of White Sands launching the first high sea rocket. The telescope is up here in the gold-plated area. And then where I met Dr. Fox was actually working on Parker Solar Probe, on that brave little cup that sticks out and finds the amazing solar wind, the wind that constantly flows off the sun, and some of the friends that I work with there before she was mounted to the spacecraft. And I also work with telescopes, so not only sampling the plasma in situ, but have had that history of looking at the beautiful images of the sun and communicating that to the public. Next slide, please. And so my career path, I studied physics and astronomy at the University of Michigan. I took a year off to industry and to figure out kind of which science I wanted to do. I then decided to go back, actually for a master's degree, but the administrator of the department convinced me that I should just sign up for a PhD, just see what happens. And there I was taking qualifying exams and getting a PhD from the University of Michigan. And I then got a postdoctoral fellow at the Smithsonian, and then was moved up to a full staff scientist, Smithsonian astrophysicist. And from there, came to NASA as a program scientist. And this looks like I had some amazing plan, that I went to the right universities and I did the right things, and everything was leading to this wonderful job that I have right now. But if we go to the next slide, we'll see how that actually happened. So I got my physics undergrad, and I actually followed a boyfriend, and that's why I went actually to get the industry job. I enjoyed my industry job, but it really was to have that life balance that I went and took that time off. There was some cool science there, and I was really stubborn. And I decided that I was actually going to go back because said boyfriend said I couldn't get a PhD. So I decided to prove him wrong. So I went and got a PhD in space physics because I thought it was really interesting. But during that time, I had depression. There was imposter syndrome, like Nikki talked about, that just didn't feel like I was quite good enough or didn't fit in. But, got this chance to study as a postdoctoral fellow at the Smithsonian. So I went to Cambridge. There was amazing things. There was joy, there was friendship, there was dancing, there's lots of great things. And finally got a job as an astrophysicist. And it wasn't that easy. There was definitely thought of leaving the field, doing other things. And even when I had a job, there were failed proposals, but there was still curiosity. The sun gives us so much interesting things. The space weather that affects all of our lives was just interesting. So I stuck with things that interest me. Working on Parker Solar Probe was very interesting, very challenging. It brought together my engineering side and my physics side. So this was something that I just kept following my passion, and went through various rocket launches. There's also family and shiny things. And then during the pandemic, found a NASA program scientist job to really work now on missions going forward. Talking about the GLIDE mission was mentioned earlier. It's actually going to look at the Earth and kind of how its atmosphere breathes during space weather, how the water leaves or doesn't leave the Earth's atmosphere, which is important to everyone. I also get to work on mentorship, which is something that is very near and dear to my heart. So I've been able to combine a whole bunch of different interests into one amazing position. Next slide. Now to Amy.
Hi, everybody. Hi, everybody. My name is Amy Weinberger. I'm so excited to talk to you today. My story is so similar to the people who've already spoken. I decided I liked math and science in high school. And as a high school senior, I took physics and I fell in love. Just like you fall in love with a girl or a boy, I fell in love with physics. And this is my high school picture in 1991, and that's what we call Molly Ringwald hair. If you don't know who Molly Ringwald is, ask your parents. They'll know who she is. But I had Molly Ringwald hair, and I loved physics. I was the only girl in my college physics classes, but I still loved it. I persevered. When I went to college, I did this really cool thing. I went away for a summer, and I did research somewhere else. And when I did research at that other place, it was the Smithsonian Center for Astrophysics, the same place that Kelly was just talking about. I stepped in, I wandered into this guy's office, and he was a solar physicist. And he taught me about the sun, and I started loving the sun. I was so excited. So that really helped me understand where I wanted to go with my life. I just wandered into somebody's random office, and that person is my mentor. I still talk to him. I talked to him yesterday. So you never know when you're going to meet the person. You never know when you're going to fall in love with the field that you're going to fall in love with, and you never know when you're going to meet a person who's going to change your life. Okay, so I went through different colleges, I went through different jobs, but in 2010, I came and I started working for NASA. And the reason that working for NASA is the coolest thing, if you'll hit return, Nikki, is that I got to be a rocket scientist. So not only do I get to work at headquarters with these great people that you've been hearing from, I get to launch rockets. I'm so excited to launch rockets. And this is a picture of me during my first rocket launch. If you'll go forward, Nikki. Oh, I also had kids and family, all the other stuff along the way. But one of the reasons that NASA launches rockets is because we need to get above the Earth's atmosphere to observe the sun and other astrophysical objects. certain wavelengths of light are absorbed by the Earth's atmosphere. So which is great, because if they came through the Earth's atmosphere, they might hurt us. So the atmosphere is great because it protects us, but it gets in the way if you want to make observations. So we launch these rockets, we get about 5 minutes of observations, and then the rocket comes down and it lands and the parachute opens. Now this cartoon makes it look like it's really simple, but it's really, really fun in person. If you'll hit the return, we'll watch a quick movie of what a rocket launch is like in person. You only get about 5 minutes of observations when you launch a rocket, and it's the most exciting 5 minutes of your life as a scientist, for me at least, because then you can be in the control room. You get to wear these cool ear things. If you'll hit to the next slide, Nikki. You get to wear these cool ear things. You get to talk to all the other people. It's very cool. You're in mission control. So this is a picture of me a couple of years ago when we launched a rocket with 2 other women that were my co-leads of this rocket. And that gentleman standing beside me, that's the gentleman I wandered into his office when I was 21 years old, Leon Golub, who's still my mentor. That's how I became a solar physicist. So my advice to you guys would be take lots of science, find something that you love to do, that you're passionate to do. Always bring your A game. You never know who you're going to meet that's going to change your life. And come work at NASA. NASA is the best place to work. That's all I have. Thanks, Nikki.
Thank you so much, guys. So I'm just going to wrap it up by saying, I really hope you're inspired by the people you just heard from. I think they're all amazing, and I have to say I loved hearing their stories. Sitting here this morning, I had a few tears wiping away there. But as I said at the beginning, the key to being a scientist is to love answering questions. You do not need to know everything. You don't need to have all the answers, but you do need to have that real curiosity and that passion. But NASA is more than a group of scientists. What is so inspiring to us is no matter what people's role is, everybody feels like they're part of a NASA mission. 2 summers ago, I was at Kennedy and I was walking around. I had my NASA garb on because I was giving talks, and a guy comes up to me and says, hey ma'am, how are you doing? I said, good. He said, you work for NASA? I said, yes. He said, so do I. I said, oh, great. What is it you're doing? He said, I'm part of putting the first woman and the next man on the moon. And I said, oh, great. What is it you do? He said, I'm a custodian. But he had that just general love and passion of being part of the mission. It didn't matter what he did. He was helping NASA achieve more. And so, there is such a tremendous and rich diversity of roles that are necessary to get a mission into space. And it's an area where so many different types of people and jobs come together. So really, if you love space, then there is a career for you at NASA. But hey, maybe NASA isn't for you. And as I think you've heard from my friends, the important thing to do is something you're really passionate about. Pretty recently, I realized what was important to me was not so much the science of the missions, but it's that I get to work in a place where the priority is a team that works together. And I'm convinced that the best way to create and maintain diversity is to make a team where implicit and explicit bias is minimized and people can be heard and achieve their merits, no matter what they may feel about their inherent welcome. They have to feel welcome. They need to be welcome at the table so we can all work together. And as you've heard, it's okay if you don't know what you want to do with your life. It's also okay to change the direction or the career in life if you want to. You'll know the right choice for you. The worst thing to do is not make a decision. Make a bad decision. You can recover from a bad decision, but the worst thing to do is not to make a decision. I have a friend who's a principal investigator of a NASA mission, and she says she never wanted to work for NASA. She had a winding career path. She started from a science undergrad. She went to a business consultant. She worked in magazines. She ran her own little company writing business plans. Then she lectured in math. Then she ended up going back for her PhD at 31 when she was a single parent. Now she leads a NASA mission. And so, there's no real aha moment. There's no single track. I'm sure if you've seen, particularly from the way Ali and Kelly had their slides laid out, if from the outside someone's career path looks like you can connect all the dots in an obvious fashion, it really doesn't mean anything was obvious at the time and that they didn't have letdowns or redirections along the way. So keep showing up and remember that progress is made by sheer stubbornness. And so I'm just going to leave you with a thought that we are all explorers, and exploring space is an opportunity to not only discover new worlds and build advanced technologies, but to really work together toward a larger goal, irrespective of nationality, race, or gender. And if we stop exploring, we will stop being human. So just, close your eyes and remember, if you can't imagine it, then you can't be it. So close your eyes, use your imagination, dream big dreams, and you're going to go far. Thank you so much for your attention this morning.
Thank you, Dr. Fox, and your team so very much. We do have a few questions, and we've been granted permission to go just a little bit longer if you'd like to address any of those.
Sure, that sounds great.
Okay. Some of the attendees wanted to let you know that they did watch the eclipse at beaches, several beaches in South Carolina, and towards the center of the state in a place called Greenwood.
Great.
And then you have lots of questions about the Parker Solar Probe. I think one that sort of follows up about the heat shield was asking if there's anything in its design that helps the heat shield radiate heat away from the craft into space.
Yeah, so actually the coating itself, that white coating on the front really helps it radiate the light back, so it kind of reflects it. We do have a cooling system on the spacecraft, but that is actually really there primarily for the solar panels themselves, for that water that runs through the solar panels. So we do radiate heat out from that, but the actual heat shield itself kind of gets rid of the heat. It's made of two very thin face sheets of this carbon kind of like the graphite epoxy. They're very thin, so it's about we lovingly call it our 6-foot frisbee, because it's about 6 feet in diameter. It's about 4.5 inches thick, and in between those two thin face sheets there is a region of foam that is also a carbon composite, but it's a very low density foam. So it's about 99% air when it was here on Earth. Anyway, obviously there's no air in space, so it becomes a much more stable thing. But between all of these layers, and then there's also a big kind of air gap or vacuum gap from the back side of the heat shield before we get to the spacecraft itself. And there's so little heat that is actually conducted from that heat shield. The whole thing is actually attached by just 6 carbon bolts. And so there's a structure that holds that heat shield in place. It's a titanium welded structure that was also specially designed for Parker Solar Probe 2. And there are just these 6 little joints that hold the heat shield in place. And again, they're kind of like ball joints, like your shoulder. So that means as the heat shield kind of bevels and bows and changes shape in space due to the different temperatures on it, it doesn't sort of fly off. These joints will hold it in place. They're movable. And so there's hardly any places for the heat that's actually contained in the heat shield to conduct into the spacecraft itself.
Thank you. There's another question that follows up and asks, if the intensity of the light is the primary source of heat, does it follow that you want the shield to be as reflective as possible, or is a matte finish more efficient?
So that's a great question, and there's different. So for us, for Parker Solar Probe, we have the most reflective we can with this sort of whiter than white, and it really is a glowing white. I realized I didn't have a picture of the spacecraft with the heat shield on it, but if you Google it, you can see pictures and you'll see just how white that coating is. Interestingly, Solar Orbiter has they have a black heat shield. It's more like a sort of charcoal cover, and that's because they actually absorb their heat. So they chose not to, but they're nowhere near as close, and so the heats they deal with are very different. But they actually used something that absorbs. We use something that reflects to the maximum amount possible.
All right, thank you so much. Our next question is asking about your S-shaped switchbacks, that they seem like they are showing ionized particle streams traveling at different speeds, like eddies in fluid dynamics. Are the factors that influence the speed of solar winds well understood, or could we fill in the space in between the rays and that animation such that the S-shaped switchbacks are actually wave fronts and ripples in a field?
Yes, golly, that's such a smart question. And yes, you're exactly right. I mean, that's just a graphic. There are field lines everywhere. We always draw magnetic fields as like lines, but really they're, it's a full force. It's not just single lines that form. But yeah, these are very small discrete features. And exactly, if you think of the solar wind kind of as one flowing river, these are little sort of eddy currents. I mean, they're little features that are happening in the general flow. And they're magnetic fields that, as the fields are coming back, they're actually sort of rotating back and flowing back towards the sun and then coming back out again. So they really are discrete features in kind of a sea of solar wind. And I'm going to ask Kelly if she wants to add anything, if she can just pop her microphone on.
No, I think you got it.
Okay, all right.
Okay, 2 more questions. The lighter question is, how many times have you suffered through some version of just travel to the sun at night joke about avoiding the high temperature issues with solar exploration?
Oh, not only have I suffered through it, I've actually used it a couple of times. I hate to admit that, but it usually works really well on radio shows. But so I often get the question, somebody will say, well, how are you going to deal with the intense heat? And we're going to go at night as the obvious answer to it. But yes, I have suffered through it a lot, but I do use it myself. So I'm a ham, really I am.
Wonderful. Okay, our last question. Why do you have to despin a payload in a rocket launch, and how do you do that? How fast is the payload spinning after launch?
Oh, golly. Allie, I'm going to get you to do this one because they're all different. So give me an average answer. And then actually, Amy is going to have an interesting answer from rockets too. But Allie, why don't you take that one?
Yeah, so spin stabilization is basically attitude control for a spacecraft, a rocket, a plane. And what I mean by that is, pitch, yaw, roll. So if I had my camera on, I could see what pitch, yaw, and roll is. But there are 3 different ways that a vehicle can move. So whether it's spacecraft, for a spacecraft, for instance, there's 2 ways to stabilize. You could spin stabilize, or you could use 3-axis stabilization. 3-axis stabilization usually means you have little thrusters or little rockets to control the movement of your rocket or spacecraft. And sometimes just spinning it, spinning the craft, whether it's a spacecraft or the rocket, will stabilize you. So depending what you have, the rate of spin is very different for spacecrafts and for rockets. It all depends on the thruster move. But like I said, I could let Amy have her story about the spin, but that's usually why you spin up and despin the spacecrafts or a rocket or an aircraft, a plane. That it is to control that yaw, pitch, and roll.
So Amy.
I'll just jump in and say that you want to despin if you're looking at things like the sun, because if you're taking a picture, you don't want to be rotating while you're taking the picture. And on sounding rockets, we do exactly what Ali says. We have these little jets on the side, and we just use compressed air, and that's what helps us stabilize.
All right, thanks, guys.
Thank you all so very much. Really appreciate your time today, and our first breakout sessions 1 through 5 start at 1:15, and we certainly look forward to all of the presentations that are coming up. Thank you.
Thanks, everybody.